Hello all, welcome to this talk where we will revisit Taylor-Culick retractions. My name is Abdallah. I'm a postdoc at the Physics of Fluids group at the University of Twente, and this work was done together with Vatsal Sanjay, Paul Kant, and Detlef Lose. A quick recap of the previous talk, if you were not there. We studied the viscous dissipation in classical and two-phase Taylor-Culick retractions. So the classical Taylor-Culick system is defined as this. We have a water film retracting in air from left to right, where the density and the viscosity of the surrounding medium is not that important. We had the control parameter in that case would only be the owner's organ number of the film, which is water, while in the two-phase scenario, we have a water film surrounded by oil. Here, the density and viscosity of the oil phase is also important. And we have two control parameters here, the owner's organ number F and the owner's organ number surrounding, where eta denotes viscosity, rho denotes density, and gamma denotes the surface tension. The response parameter is the Weber number of the retracting film, where Vf is the film retraction velocity. For the classical case, the Weber number of the film is identically 1, while for the two-phase case, we have an inertial regime where the Weber number is independent of the owner's organ number, and a viscous regime where the Weber number goes as 1 over owner's organ number squared. So we can define a Weber owner's organ phase map where the classical Taylor-Culick regime is given by this line, same as the inertial part of the two-phase Taylor-Culick regime, while the viscous two-phase Taylor-Culick retraction is given by this line here. It's given by Weber goes as 1 over owner's organ squared. So this is the state of the art. We can also represent this dynamics in a capillary owner's organ phase space where we can replace the film velocity with the surrounding velocity, knowing that they are equal in the steady state. And the capillary owner's space looks like this. So to summarize, in the inertial regime for a two-phase Taylor-Culick retraction, the Weber number is constant, while in the viscous regime, the capillary number is constant. We now move on to studying a three-phase Taylor-Culick regime where the water film is sandwiched between air and oil phase. The motivation comes from studying large-scale oil spills and also where oil droplets may rise up to the water-air interface and rupture the water film. So our experimental setup looks something like this. We have a water bath and an oil droplet here, which we inflate very slowly, which in turn makes this water film progressively thinner. At some point it ruptures. We capture it through a high-speed camera. So in a typical movie, you'll see this is the point of rupture. And now if I play this movie, you'll see that the water film here ruptures and spreads radially. This was done for a viscosity of 10 centistokes, so 10 times as viscous as water. I played the movie here again. We can also increase the viscosity of the oil phase. Here I show you a movie for 100 centistokes, that is 100 times as viscous as water. And you can see that the dynamics is slower, which is expected as the viscosity increases. We can also track the rupture diameter here and plot it with time. So this is how it looks for a typical case. We vary the viscosity, and these are all the experiments that we did in this study. Note that the retraction becomes progressively slower as the viscosity increases, which is very much expected. We look at the very early times of this retraction. So in the early time, for all the viscosity that we have tested, the retraction is linear, and from this we can get a slope which denotes the retraction velocity. We can plot this retraction velocity as a function of the oil viscosity here, and these are all the data points from our experiments, and we can see that this nicely follows a -1/2 scaling. So basically the retraction velocity scales at viscosity to the power -1/2. Now the question is, can we understand the scaling for this retraction velocity? So just to recap, this is our three-phase retraction scenario here, and we have two owner's organ numbers, the owner's organ film and the owner's organ surrounding. We modeled this in numerics. My colleague Vatsal does numerics on this in Basilisk. So this is our scenario. We start off with an oil-air interface here, and here is our water film. Note that our numerics is initiated such that there is a precursor film of oil covering the water-air interface. These are our typical numerical snapshots. On the left, I show you the velocity contours normalized with the film retraction velocity, and on the right, I show you the viscous dissipation contours. Note that at low owner's organ S or low oil viscosities, the retracting film digs into the oil phase because of an imbalance of surface tension between lower and upper interfaces, but as the viscosity increases, this effect is less pronounced. Also note from the viscous dissipation contours that the dissipation is very much localized near the retracting tip. So these were the dynamics we were identified from the classical and two-phase Taylor-Culick retractions. Now we plot our experimental data points for the three-phase Taylor-Culick retraction, and these are the black data points here. We also did some experiments with water glycerol, and they also are shown here. And our numerical simulations for the three-phase Taylor-Culick retraction agree very well with our experimental data points. And we also identify a new scaling regime here where the cavity number scales as the Ohnesorg number to the half. So to understand the dynamics, we look at the energies here. So the surface energy goes into viscous dissipation, where the rate of change of surface energy is equal to the rate of viscous dissipation. The rate of change of surface energy is expressed in this form, while this is the viscous dissipation here. Now, we know from our contours that the viscous dissipation is very much localized. So this is our total viscous dissipation here, but we need to identify where the viscous dissipation takes place. So we define a local viscous dissipation here, where this R denotes a distance from this three-phase contact point here, and this AP denotes an area with the radius r. We non-dimensionalize everything with H0 and the viscocapillary velocity. So our non-dimensional local viscous dissipation is expressed in this form here. We can calculate the non-dimensional local viscous dissipation per retracting length, and it's expressed in this form. We can now plot this quantity here as a function of the radial distance r, and you can see that for certain time the viscous dissipation increases and then becomes constant. We can write now that the total viscous dissipation is the local viscous dissipation at a limit where r goes to infinity, and you can see that the total viscous dissipation here becomes basically constant as time increases. We can now plot this as a function of the Ohnesorg number here, and we get a slope of half, which basically means total viscous dissipation per unit retracting length goes as Ohnesorg number to the power half. Now the rate of change of surface energy is equal to the rate of change of viscous dissipation. We non-dimensionalize everything in the same way again. So this is our final equation here. We introduce the capillary number here again, and this is here, which we simplify to show that the capillary number goes as Ohnesorg number half, which was also what we saw from our experiments and numerical simulations. We can also recast our entire phase space in the Weber-Ohnesorg space, and you can see we identify two distinct scaling laws here for the Weber-Ohnesorg space. For the two-phase retraction, it's Weber goes as 1 over Ohnesorg square, while the three-phase scaling is Weber goes as 1 over Ohnesorg, and these scalings are Ohnesorg F independent. Basically, this shows that for the three-phase retraction, the local viscous dissipation governs the dynamics of the retraction. With this, I would like to thank you for your attention. Please feel free to reach out to me over by email for any questions that you may have. Thank you.